Hello, welcome to another problem session. So today we're going to talk about a problem concerning Halley's Comet. You might have wondered how we kind of get a whole bunch of properties of orbit just by observing planets and comets and things like that. So this will help you get that handle on that. We're going to make just two observations. Of course, observations are made based on Earth, and then you can convert that to observation made with respect to the sun, right? That part I'm not covering here, but it just so here are two observations. So this is one is perihelion. So I make an observation at perihelion. So this is one data. So one data, and another data is when it's at 60 degrees over here, that angle, when it's over here, how far away from the sun it is. So these are two observations we're going to make, and from these two observations I will be able to answer all of these questions based on what we have derived using Newton's laws of motion applied to gravity. So let's do number one. How do I get the eccentricity of this orbit? This is actually not drawn to scale for Halley Comet, because Halley's Comet is, this other part is very far away, okay, and this is kind of like that. Okay, so let's use our equation that we have deduced. So r at any time is equal to some constant r0, 1 minus this eccentricity constant cosine theta at this. So you have to know what theta and r refer to. So they refer to this coordinate system. In this coordinate system, we place the origin here, and this is along the x-axis, this is along the y-axis. At any time t, the angle theta is this, and the distance r is that. So that's what these things refer. And these guys are constants. So they're related to that in this equation. Okay. So we've given 2 points. This is point, say, 1. And this is point 2, and in point 1 theta is pi and r is rp. Let's call it rp. That's perihelion. I'm not going to put this number right away, just use it. So when it's rp, r0 is unknown, 1 minus cosine is pi, cosine pi, and this is minus 1, so it's r0, 1 plus epsilon. So this one equation we get, equation 1, and then over here, when it's over here, that distance is, let's call it r2. So for that distance, r2 is same r0, 1 minus epsilon, but this angle is given, so the angle that we want is that angle, so that's the theta 2. So theta 2 is pi minus pi over 6, so this is cosine pi minus pi over 6, or pi over 3, I mean, not pi over 6. 60 degrees pi over 3. Now if I expand this, I'm going to get r0, 1 plus epsilon over 2. You can expand this and you can see cosine pi over 3 plus sine pi over 3, and this is 0, and this is half, and this is minus 1, and this is half, and that's why I get that. Now here we know these guys we'd given, and we're supposed to find epsilon. So I can take a ratio and solve for epsilon, right? So take ratio. So R2 is bigger than RP, so let's take R2 over RP. We're going to get a ratio from there, and it's going to be just 1.2 over 0.9. And on the other side, 1 plus epsilon will flip up, and then you get a 1 plus epsilon over 2. You can see I can solve this for epsilon, so I'm going to rearrange and solve it and come back. Okay, so I have actually did the calculation, and I need to make some correction over here. This is 1.2. Originally, when I did the calculation, I simplified a little bit, and it just leads to epsilon equal to 1. So instead of that, I would use this number, and this number actually gives, after you cross multiply and simplify for epsilon, epsilon will be 0.97, very close to 1. If you use the original number, it is epsilon equal to 1. So that's the answer for this. Let me check the book for exact value, that's published value for eccentricity, and I think it's 0. Published value is 0.967, and I just did some calculation. So, but the important part is the process by which I can use 2 data points to find the eccentricity. Okay, so we're done with 1, and I'll make a note of that eccentricity for us is 0.97 as an answer, and I'll clean this up and try to answer other questions. Okay, the next to answer is what is the distance to the aphelion, the furthest away. So you can see that to answer this, you have a perihelion was R0, 1 plus epsilon. So aphelion is this place, and this is the sun. So this distance is in direction of theta equal to 0. So the R aphelion, this is the R aphelion, that will be R0 or 1 minus epsilon. So R0 still is unknown, so just take a ratio of this. So RA over RP will be 1 plus epsilon over 1 minus epsilon. And so RA will be this stuff here times perihelion. And we have the answer here is 1 plus, I'm going to use mine, 0.97, and 1 minus 0.97 times 0.9 times 10 to the power 11 meter. Okay, so we just do a calculation and I'll come back and give the answer. So this is 5.91 times 10 to the power 12 meter. You can see very far, 10 times as far away. So let's do the answer here, and RA is 5.91 times 10 to the power 12 meters. Okay, I'm going to clean this up and do number 3. To answer 3, we have to answer 3. We remember the third law of Kepler. We can do it if one way to do it is use Earth's data, but you don't need it here. You actually are just use data given from this data alone. If the Earth data was given, we will just use T of Halley comet over T of Earth, which is 1 year. The square is going to be same as major axis for Halley, which will be this will be R aphelion plus R perihelion divided by 2, and then same thing for Earth cube. So you can use Earth data if same as the axis for the Earth, which will pretty close to circle, so you can use just radius of the orbit. It could be pretty good approximation, and we already got those guys, and so we can get TH from that. That's normally how many problems solved here, but we can just use our current data. So if you remember, the formula for T square of any orbit was 4 pi square a cube over g times mass of the sun plus mass of the planet, or mass of planet, or mass of planet, or mass of a satellite, comet, etc. So that's, now we can say that this is the Halley's mass and this is the sun mass, and we can say that this is this part we can approximate is mass of the sun. Now the mass for this, you have to be given mass of the sun. Okay, for this we need Earth's. So now there is this question about, can you deduce the mass of the sun from the data? So if we could find this some other way, then we don't need the mass of the sun. Like if I get this from here, then I will need the mass of the sun. So I'm gonna because there later on we do get the mass of the sun question, I'm gonna say we either have to remember this of course you remember, and then this one we have to remember it somehow. Okay, and I'll just look up the data. I'll give you the data for the Earth from Earth's data. So I'm going to look up online and get the okay, I looked up this data, and we can use the data now. We can use the data for this as a meter, because everything is, this is given in meter, so this one we can do in the meter, and everything simplified. Usually so many digits here, we can just say 1.5 times 3 powers coming from here, 6, 9, 11. So you can see same kind of order, so we don't have to carry much. And so from here you can say the Halley comet H will be AH over AE divided by 3/2 times T Earth. So that's many years. And AH is you have this plus this divided by 2, so you can say 59.1 in using 10 to 11, 59.1 plus this is 0.9, and that's going to be 0.60. I'm going to divide by 2, so that's like a 30, and A Earth is 1.5 in this 10 to the 11 powers, and 3.2, and this is 1 year. So if I work this out, what does it become? Let me do the calculation. When I work this out, I get an answer which is 70. Let me look up one more time the answer. answer I got was 89 years. I calculated there, and so 89 years. Which is of course not correct, you know. So this is not correct. Actually, it is 70. I think 76 years. I believe 76 years. But it's pretty. It's in the ballpark, you might say. So where is the mistake here? You can trace it. Is this is correct? So the mistake must be in this guy. So mistake is in this guy or this guy. So you can trace it. You can see our data here is these data probably are off. But nonetheless, given those, we will get 89 years. Okay. So this is although not correct for the Halley's Comet, but this is the procedure by which we can find the period. And because of the data being off, even a little bit of decimal place off can throw a lot of things. Eccentricity is very sensitive to eccentricity, and 0.97 is not the same as the 0.96 something. Okay. In any case, this is one way to do this, and then let's do 6 before we do other things. Okay, so to do the 6, now if we got the period t, we can get the mass of the sun, and we all know what A is. A is 30 in these units, right? So for us, it is t is, I'm going to use 89 years, and all of this has to be converted into seconds. So you can see, to get the mass of the sun will be just t square. Just switch this, 4 pi square aq over g, because I'm going to ignore Halley Comet's mass compared to the mass of the sun, g times t square of the Halley Comet, and this should be the mass of the sun. Incidentally, you don't need Halley's Comet to get the mass of the sun. This you can apply to, say, for the Earth. For the Earth, you can guess mass of the sun from 4 pi square a Earth cube over g, Newton's gravity constant, and time period square Earth. So this one we have much more accurate, and this one of course came out a little bit off, you know, almost 13 out of 76, like a 20% off. That's a lot off because of my using kind of a little bit wrong numbers. Okay, so this is how you can get sun, and you can plug in the numbers and they will be off just like this was off because we're using off numbers. Okay, so we've done 6 and we've done 3. Now the interesting parts are 4 and 5. Okay, so I'm going to clean up this and look at that. Okay, so this is a very interesting question actually. When it is at a distance of perihelion and its speed is vp, you can see its angular momentum will be mass of the mass of the comet times rp vp. So this is known, this is not known, and this is what we have to find. Okay, but L is also in the definition of R0, if you remember. So R0 was L square over mu times alpha, and mu is G M M. I'm sorry, mu is not that. Alpha is G M M, and mu is M M over M plus M. Okay, so if I make this guy L square, it's going to be mu alpha R0. We don't know R0 yet, but because we know epsilon and we know RA, we can get so R0 over 1 plus epsilon is the R perihelion. So I can get R0. R0 is just RP times 1 plus epsilon. So we can get R0. So you can get R0. And so if this is the case, let's use this for L square on the left side. So we have M square, RP square, VP square, and on the right side I have a mu alpha R0 is RP times 1 plus epsilon. Okay, let's replace these guys with this M over M plus M, and alpha will be G M M. So this thing is all on the right side. You can see that this M, let me get a different pen. This M cancels this M square. This RP cancels one of the RPs. And we have got an equation. This M is almost like M. So this whole thing will cancel this M, but it will leave this M around. So let's see what's left. So VP square is RP goes on the other side. You have a G M 1 plus epsilon over RP. Okay, so now we can just take a square root of this. So V at perihelion is a square root of G M 1 plus epsilon over RP. And this is the mass of Sun. So we are we worked out the mass of Sun in 6, and we can just use the data or just look up the mass of the Sun. And I'm just going to look up the mass of the Sun in the internet. Okay, so we have this numbers I put in and try to calculate it out, and then we have a 54,000 meter per second. It's like a 54 kilometer per second. That's pretty fast it's going, and that's I think this is pretty close to the correct answer here. So we have number 4 also done, and now I want to do number 5. So for number 4, let's write down V at perihelion is 54 kilometer per second. Okay, so now I'm going to erase this and come back and finish up. Number 5 is quite easy actually. Number 5 is very easy using 4 and conservation of angular momentum. So L is M when it's at the perihelion, speed of perihelion. It will be M aphelion. So you can see It's the same L, but two different formulas, and we want this. So V at aphelion is just gonna mass gonna cancel out. Rp over Ra times Vp, and you can see this is 59.1 in 10 to the 11, so 59.1 times 10 to the 11, and this will turn 11, so they're going to cancel out. 0.9 times 54 kilometer per second. 54 kilometer per second. And so you can see that this is almost like a 600 times that. Rp Vp this should be exactly opposite of this, so I think we're messed up here. Actually this is just opposite. Okay, this is 0.9 and this is 59.1. That makes sense now. So this is 1, so about 60 times less. So 54 over let me. So I said it was easy, right? I'm very easy, but you can make a very silly mistake like this, putting these numbers in. We have to be careful. I was able to catch it because I was expecting very slow and it was getting very large. That's just the opposite of what it should be. So it's about 65.7 kilometers per second, and that's pretty. It's not that fast. So over here, it's going at 54 kilometer per second, and over here it's going at 0.8 kilometer per second. And you expect that's the case, right? Because in same amount of time, this thing will be going very slow, because this area has to be same as that area. This is Kepler's second law. So over there has to be slow compared to that. Okay, this is a pretty complete description analysis of a lot of features of orbits that you may be presented with, and in some other settings you may have to deal with different types of situation. So for instance, if we deal with satellite, so this will be Earth, and there will be satellite, its orbit will be also elliptical about the Earth, and a lot of this, where you use mass of the Sun, you will use mass of the Earth, and this is mass of the satellite. And you can place center of the Earth at the center of mass of the two systems, because satellite will be much less mass than the Earth. So this system, I will try to do one problem like that as an example, but this is, and Halley's Comet is more or less the same example. I will stop here now. I took a long video to cover a lot of the aspects of calculation that go into doing calculations concerning comets and planets. So I'll see you in another video. Bye.